In this video, we'll talk through the notes for section 2.5, which is called Sources and Duhamel's Principle. The question is, how do we solve a PTE if there is a source term present? For example, consider the diffusion problem with a source that you see here. So we have the heat equation, but we've added a source term to it. We're also assuming that our initial condition is given. We're just calling it 0 though. U at x comma 0 is equal to 0 for all x. So we're going to make use of something called Duhamel's principle. It states that a particular solution to an inhomogeneous linear differential equation can be computed from the solution to the related homogeneous differential equation. This is something that you would have seen when you studied ordinary differential equations, although you probably wouldn't have heard it by that name. Instead, what you would have done when solving a non-homogeneous linear ordinary differential equation is first start by finding the solution to the related homogeneous linear ordinary differential equation. And then you would have used that to find the solution to the non-homogeneous problem. We're going to show that you can do something like that with partial differential equations as well. But let's start with an example from ordinary differential equations. Look at the initial value problem here. Here we have a differential equation which is first order linear and non-homogeneous. That is, as long as we're assuming that f of t is not constantly equal to 0. So it's not 0 for all t. Otherwise it would be homogeneous. And we have an initial condition y at 0 is equal to 0. This is first order and linear, so we can solve it using an integrating factor. In this case, we multiply both sides of the equation by e to the at. And this gives us our integrating factor, so then we can write the left-hand side as the derivative of a product in the usual way. Then you integrate both sides, and then you get that e to the at times y is equal to the integral of e to the at times f at t dt, which, as we usually do, we write that as a definite integral plus some constant of integration. So our general solution to the ordinary differential equation is given here. Remember that you just have to divide by e to the at or multiply by e to the negative at, depending on how you prefer to describe it. But now we have a general solution to the ordinary differential equation. Y is equal to e to the minus at times this definite integral. The integral from 0 to t of e to the as f at s ds, where s is just our dummy variable. Now this is just the term here. This is the antiderivative of e to the at f of t. We don't know what f of t is, so we can't write down an explicit antiderivative. So instead we write down the antiderivative in terms of a definite integral. The next thing we do for the sake of simplification is we multiply this e to the minus at, we bring that into the integral. So that gives us e to the minus at times e to the positive as, which we can simplify as we have done here. That means that y is equal to the definite integral from 0 to t of e to the minus a times t minus s times f at s ds plus this constant times e to the minus at. To find the value of c, we make use of the initial condition. So the initial condition is y at 0 equals 0. So if you plug in t equals 0, then you get a 0 in the upper limit of integration. You also get a 0 here, which apparently I forgot to put in. So that's also 0. However, that doesn't really matter because what's important here is we have an integral from 0 to 0. And when you integrate from 0 to 0, you just simply get 0. This other term involving the constant, c, it's multiplied by e to the minus at, but of course t is equal to 0. So we have another 0 here and here. Let me just highlight that one. So what do we end up with? We end up with c is equal to 0. So that means our constant c is equal to 0, so the solution to our differential equation is just the definite integral. The integral from 0 to t of e to the minus a times t minus s times f at s ds. That's the solution to our initial value problem. Now we make an observation. Let w at t comma s be equal to e to the minus at times f at s. Now notice that this is almost the same as the integrand. In fact, y is equal to the integral from 0 to t of w evaluated at t minus s comma s, because w at t minus s comma s is exactly this integrand, e to the minus a t minus s f of s. So we're defining w at ts so that the integrand is w at t minus s comma s. So we're going to make a claim about w. W is the solution to an initial value problem related to our original initial value problem. And in fact, what we'll see is that it satisfies the same differential equation. Now let's just remind ourselves what the differential equation was. I'll scroll back here. So our differential equation is right here. dy dt plus ay is equal to f of t. So what we'll see is that w satisfies the same differential equation except the homogeneous version of it. It will satisfy the differential equation with a 0 on the right. So let's show that that's true. We just need to compute the derivative with respect to t and add a times w to it. So let's just compute these. So w is right here. This is our w, so let me just rewrite it here. W at t comma s is equal to e to the minus at f of s. Now throughout this discussion, when we're computing this differential equation, we're going to treat s as just constant. So we're computing the derivative with respect to t. You can think of s as not a variable so much as a parameter. So we compute the derivative with respect to t, and s is constant, so that f at s term is also constant with respect to t. So we just differentiate e to the minus at, and the negative a comes down. So that's what's right there. So it's negative a times e to the minus at times f at s. And w, of course, is just e to the minus at f of s. So if we compute the partial derivative of w with respect to t plus aw, what you'll get is that all of these terms will cancel out and you'll get 0. So it satisfies the same differential equation, except it's the homogeneous version of it. So w satisfies the same dE as y. Well, again, it's not the same. The same differential equation as y, except it is the homogeneous version. And there's also something different to do with the initial conditions. Notice that if you plug in t equals 0, so t equals 0 right there, you lose the exponential term, and so you just end up with f at s. So w satisfies this initial value problem. So the differential equation, again, is the same, except it's the homogeneous version. Homogeneous version of the differential equation. And the initial condition now contains the source term. So the source term is now in the initial condition. We moved it away from the differential equation and into the initial condition. So this gives us a theorem. The solution to our initial value problem that we started with is given by the integral from 0 to t of w at t minus s comma s ds, where w is the solution to the related initial value problem with the homogeneous differential equation, where the source term is in the initial condition. So this is an example of Duhamel's principle at work. So now what we want to do is we want to apply these same ideas to the heat equation with a source term. So we start with this differential equation, which is the heat equation, except that we have an additional source term. What we want to do is the same thing that we just did. We want to transform this into a statement about a differential equation that is homogeneous, where the source term goes into the initial condition. That's what we're going to do. We expect the solution to have the same form. So u at x comma t is equal to the integral from 0 to t of some w. Now w is going to have 3 arguments. It's going to have an x term, it's going to have the t minus s like it did before, and it's going to have an s term. Now this s is our dummy parameter, our dummy variable or our parameter. This x is what it normally is. It's the spatial variable. And t, of course, is the time variable. So w is going to be the solution to the related homogeneous problem that we see here. So wt is equal to k times w sub xx. That's the same differential equation, but it's the homogeneous version of it. So k, of course, is our constant, constant of proportionality. And what we've done is we've just moved the source term into the initial condition. Okay, so if we define w to be this solution, then we know what w actually is, because we know how to solve this. This is a Cauchy problem. This is a homogeneous differential equation that's the heat equation on the real line, and we have a source term. So we've moved the source term into the initial condition. But we know how to solve a Cauchy problem like this. This is a pure initial value problem. And we know how to write down the equation to this this Cauchy problem. And it's in terms of the heat kernel or the fundamental solution or the Green's function, however you want to call it. So w at x comma t comma s is given by this integral. The integral from minus infinity to infinity of g at x minus y comma t times f at y comma s dy. Again, s is just some parameter in this case. We're just thinking of it as a parameter. So we expect then that u is going to be the integral of this, the definite integral from 0 to t of w. Well, not w, but it's w at x comma t minus s. Now, of course, as I write that, I realize that I need a t minus s here. Let me just rewrite that. T minus s. Because we're not integrating w, we're integrating w, but we're not integrating w x comma t comma s. We're integrating w x comma t minus s. So that t minus s goes right there. Okay, because that's that t. T becomes t minus s. Okay, so more generally, we can solve an initial value problem like this one, where we have a source term and an initial condition. In order to do this, we write it out as two separate problems using linearity. So the first problem is the one with the source term, and the second problem is the one with the initial condition. So then you can show that the solution to one of these problems is here, and the solution to the other problem is here. So maybe we should color code these a little bit. So we have that problem has this solution, and this problem has that solution. Notice that this is just a Cauchy problem. This is an initial value problem where we have a source term, but we just talked about how to solve that. So if you put those together, you get your solution to this more general initial value problem. We remark that this method can also be applied to solve the wave equation with the source term. So here's the wave equation with the source term, right here. So we have the source term f there. We have initial conditions on u and the partial derivative of u with respect to t. That's the initial position and the initial velocity. And we're assuming that they're both 0 in this case. So the solution to this problem is going to be equal to the definite integral from 0 to t of some function w at x comma t minus s comma s ds. And this w function is a solution to the related homogeneous problem where we have the same wave equation, we just don't have the source term. It's homogeneous. But we do still have a source, we've just put it here in one of the initial conditions. Notice that we put it into the wt condition, we put it into the speed condition on w. Now why is that? This source term is an acceleration. That is to say, it has acceleration units. If you go back to our original differential equation, which is up here, you have that u sub tt, that's acceleration, is equal to c squared times the second partial with respect to u plus the source term. So that means that the source term must be some form of acceleration. Now, w is itself a velocity. So u is a time integral of w, as you can see here. U is a time integral of w. So w must have velocity units, and that means that the partial derivative of w with respect to t has acceleration units. So that means that we're going to put this, that we need to put this f into the wt initial condition, because that's an acceleration condition. So it's an initial acceleration, if you will. Then by D'Alembert's formula, we can actually write down what the solution is. And we can write down the solution to this Cauchy problem here. So the solution to this Cauchy problem is given by D'Alembert's formula, and it's equal to, if you look back at the formula, you're going to have some additional terms which depend on this condition here. So the way we wrote D'Alembert's formula, we had the f term here, we had the f term here, and we had a g term here. So now f and g are swapping roles in a sense. So our g term is now called f, and our f term is 0. So if you go back and look at the formula, you'll have terms which are not being integrated, but those are in terms of this function, which is 0, so those go away. So that just leaves us with this integral 1 over 2c times the integral from x minus ct to x plus ct of this function f, of this source term. So then you obtain u by simply integrating with respect to s from 0 to t, and that gives you the solution to our initial value problem.